Evening. Today we will start with FIR filter designing by frequency sampling method. So, what are the steps? Just like in the previous methods, we need to define the filter specifications. If the frequency response they are not normalized, then we have to normalize the frequency response of the ideal filter. Okay. Then after the normalization process, we need to sample the ideal frequency response. Okay. So after we have sampled the ideal frequency response, then we have to add a linear term phase. Okay. Then we have to compute the inverse DFT. Okay. And from there we will be realizing the filter. So let us understand these steps with the help of an example. So this is the frequency sampling method. So over here what we have, design a low pass filter with the following specification. Cutoff frequency is given as 500 Hertz, sampling frequency 2000 Hertz, order of the filter it is given as 10. So alpha, from our last class we know that alpha is L minus 1 divided by 2. L minus 1 is basically the order of the filter. So 10 by 2 which comes out to be 5. So our alpha is 5 in this case. Okay. So then we have to normalize the frequency. Normalization is omega c is equal to 2 pi fc by fs. We have already discussed. So what is our fc? Fc is 500 hertz and fs is 2000 hertz. So you plug in the values. So what we get? We get omega c, that is the cutoff frequency. It is pi by 2. Okay. So determine the transfer function. We have already discussed that while we will be designing the FIR filters, we will be keeping in the passband the amplitude response will be 1 and at other locations it should be 0. So what we have, hk equals to 1 in the modulus of omega region of 0 to pi by 2. Okay. So then next step is determination of the locations and the amplitude samples. So in our last class we have seen that working in the region of 0 to 2 pi, it becomes easier for us. Okay. So what we will be doing, we will be plotting the amplitude response of say 0 to 2 pi over here. Okay. So what is our cutoff frequency? Cutoff frequency is omega by c, that is pi by 2, and a minus of this omega dash. What is omega dash? Omega dash is nothing but 2 pi minus omega c. So 2 pi minus omega c is basically 3 pi by 2. Okay. So if you look into this, if you consider pi equals to 3.14 and you compute pi by 2 and 3 pi by 2 fractions and also 2 pi. So pi by 2 is 1.57. Okay. Pi by 2 it is 1.57. Then pi we have already seen it is 3.14. Then this 2 pi minus omega c, which is basically 3 pi by 2, which is equal to 4.71. Okay, this is 4.71, and our 2 pi it is equals to 6.28. Okay, now we have to sample it. Now how do we sample it? So we need to calculate the delta k values. Okay, so delta k values, delta is the difference between the 2 points. Okay, so for computing the delta k values we need to compute the delta. So what is delta? Delta is equal to 2 pi by n plus 1. Okay, 2 pi by n plus 1, and when you talk about k delta it becomes 2 k pi by n plus 1. So this k delta it will give you the locations where delta is the difference between the 2 points. Okay, so when k is 0 we are having 0. Okay, so the first point is at 0. Okay, so when k is equal to 1 we are having 0.57. So in the frequency axis, the second point is 0.57. So in this way, we have to calculate till n equals to 10. Okay, till n equals to 10. Why? Because if you come on 11, this 11 is nothing but your 0. Because 0 and 2 pi, they are the same points. Okay, so since we are taking the 0, we will not take this 11, k equals to 11. So basically we have to change the value of k from 0 to capital N, that is the order of the filter. Okay, now if you see, we have this cutoff frequency at 1.57. So when k equals to 2, we are having 1.14. When we are having k equals to 3, it is 1.71. Now this 1.71, it is greater than 1.57, right? So it falls in the stop band. So over here, the amplitude response would be 0. That means till the value k delta of 1.14, it is within the range of 1.57. That means when k is equal to 0, 1, 2, our frequency components, they are within the pass band. Okay, similarly we will be next checking the point 4.71, where we have 3 pi by 2. So over there, what should we have? Any point less than 4.71, it will be 0. So till what point it is 0? So 4.71. So up to 4.57, it becomes 0. So when k is equal to 8, we are having 4.53. Okay, so it is less than 4.71. In the next case, when k is equal to 9, we are having 5.14, which is greater than 4.71. That means it again come into the it again comes into the passband region. Okay, so because of this thing, again 9 and 10, when k is equal to 9 and 10, it will be within the passband region. So basically, if you have to look into the frequency response, we'll be taking the frequency components when k is equal to 0, 1, 2, 9 and 10. In all other cases, k values, the amplitude response should be 0. Okay, so from here we have to now calculate the h cap k, because now we have identified the k values. Okay, now from here we need to calculate h cap k. Now what is this h cap k? This h cap k, if you see, it is given by e to the power minus j 2 pi by 11 alpha k. Okay, 2 pi by 11 alpha k e to the power minus j 2 pi by l alpha k. L means the n plus 1. Okay, so what we have, n plus 1 is 11, alpha we know it is 5, we already discussed. So what we have to do, we know the k values for which we want to find out this h cap k values. So just put the values. When k is equal to 0, this term becomes 1. When k equals to 1, you compute it. When k equals to 2, you compute the h cap 2. Similarly, h cap 9 and h cap 10, you need to compute. Okay, so you need to remember that the formula is h cap k, formula is equal to e to the power minus j 2 pi by n plus 1 alpha k. Okay, so in this equation, we need to put the k values and we need to compute the h cap k value. Okay, and once it is done, so we need to find h of n. We need to find h of n. So where h of n is given by 1 by capital N plus 1 H cap 0 is separate. Then 2 of real k equals to 1 summation of k equals to 1 to alpha. K equals to 1 to alpha. So 1 to 5. Okay. H cap k e to the power j pi k n by n plus 1. Capital N plus 1. Okay. So what you are basically doing? If you check this, and in our last class, if you remember what we did, n minus alpha. Okay, you look into the stuff. We use this n minus alpha term was coming. J 2 pi by n plus 1 into n minus alpha, that is coming. So here also we are basically bringing that part only. Okay, are you sure? Are you okay? So now if you see what we have said, so it is basically in the form of e to the power j theta, right? It is in the form of e to the power j theta, and this equation says that we only need to take the real component. So what is the real component? Real component is the cos component. So if you see 1 by 11, then 1 is h cap k 0. So from here we are having 2 by 11, 2 multiplied by 1 divided by 11. Real component is cos of 2 pi by 11 n minus 5. Okay, plus 2 pi by 11, 2 by 11 cos of 4 pi by 11 n minus 5. You got this thing? You just put the values of it's 0 1 in this way till how much we will be going? We will be going up to 5. 0 to alpha we will be going in the last class. If you see, we have gone up to 0 to alpha. So once we get these values, you can realize the filter quite easily. Okay, so this is it. Please do it. So tomorrow we'll be looking into the other things. Today also we can look into these things. At least the comparison we can look into. So comparison of the FIR filter designing methods. We have discussed about the windowing method and non-windowing method. So in the non-windowing method also we discuss about this Fourier series without window. It is basically a limiting case of the windowing method where our this window is the rectangular window. Okay, so we usually consider that under the category of the windowing method. Okay, so basic idea is that in the windowing method, what happens? It truncates the infinite impulse response of an ideal filter using a finite length window function. Okay, so it may be Hamming filter or the Kaiser filter. We will not be discussing the Kaiser filter due to the lack of time. So in the non-windowing method, we have optimal and frequency sampling method. Optimal method will be coming a bit later. So frequency sampling method we have just discussed. So over here we directly calculate the filter coefficients to meet the specific frequency domain criteria. Optimality, it is non-optimal. Okay, it can be optimal when we implement the Parks-Maclin algorithm, Maclellan algorithm. Okay, so control over parameters, indirect control. The transition bandwidth and ripple are determined by the window's shape and length. You can't specify them independently. Over here we can have precise control. Okay, so herein we can directly specify the pass band ripple, stop band ripple, and transition width, and the algorithm finds the best filter to meet this specification, and it is basically related with the Parks Maclellan algorithm. Okay. Design complexity, these are simple and intuitive, however these are more complex and computationally intensive. Okay. Ripple characteristics, largest ripples are typically near the band edges. Especially the optimal method, it distributes the ripple evenly across the passband and the stopband, and hence it is known as equiripple filters. Okay. Common techniques include rectangular, Hamming, Blackman, and Kaiser window. And optimal methods over here: Parks, McLennan algorithm, and frequency sampling method. It defines the frequency response at discrete points. So best for quick and simple design methods, and over here applications requiring stringent control over the filter. Okay. So coming to the Parks McLennan algorithm. So this algorithm, it is a computational method, and it is used to design optimal finite impulse response digital filters. It is widely regarded as the standard for FIR filter design because it produces the best possible filter for a given set of specifications. The key features of a filter designed with this algorithm is its equiripple characteristic, okay? Meaning the error is spread evenly across the pass band and stop band, and it is basically built upon the Remez exchange algorithm. So these are the some of the key steps. So I will go into the yeah, I think I forgot to add the updated PDF. Anyway, let's discuss over here. So key steps. So define filter specification. We need to define the filter specifications. So over here passband and stopband frequencies are defined. Then weighting the relative importance of minimizing the error in each band uh, is implemented over here. A higher weight in the stop band means you want less attenuation there. Attenuation means repel in this case. So filter order, the number of the filter coefficient steps which determines the filter's complexity uh, and potential stiffness. Okay. So once we have this filters thing, then we go for the initial guess. Okay. So in the after initial guess, what it does is that so what happens? We make an initial guess for the locations of the external yeah, frequencies. Okay. So after that, what we do? We go for the uh, iteration. So in this iteration, what happens? It repeatedly solves a set of linear equations to find a new polynomial that minimizes the error at the current external frequencies. It then scans the entire frequency range to find new points where the error is maximum. These new points replace the old ones, and again this iteration goes on. Okay, so this method, what it says is that suppose in your initial case, if you consider this as the time axis or the number of the iterations, say I, number of iterations I, and in the y axis you are having the errors, okay, E. So in the initial stage, once you have the initial gauge, suppose you are having some errors like this. Okay. Now, what happens over the time? It tries to minimize the error in both the pass band and the stop band. Okay. Now, what it will do is that it will try to bring the errors within a specified band, and when it is minimized, then only this iteration stops, and we call that it is coming to a convergence. And this iteration process, it is called min max method. Okay, min max optimization. So what does this min max means? Minimization of the maximum error. Okay, minimization of the maximum error. So over all the frequency components, we are basically trying to minimize the error, and we try to bring the error to the minimum. Okay, and hence it is regarded as the min max method. Okay. So pros and con advantages. So we can get optimal filter for a given filter order. It produces a filter with smallest possible maximum error. Okay, that is the ripple in the past and the stop bands. Okay, precise control allows the designer to specify the exact locations of the pass band and stop band edges. Equiripple performance, the error is distributed evenly, which is often a desirable characteristic. Equiripple means error is distributed evenly. Okay. So disadvantages: computational complexity. You can see you have to perform the things multiple time. Okay. Then potential non-convergence. It means so happen that if your primary estimate it is not close enough, then what it will do, the program not converge. Okay. And there is no control over the impulse response. The impulse response of the resulting filter is not directly controlled and may not be suitable for all applications. So then comparison between the Park MacLean's McClellan algorithm and the frequency sampling method for designing the FIR filters. So the designing philosophy in Park's McClellan algorithm creates an optimal filter that minimizes the maximum error. Okay, so from here this min max method comes. Okay, so in the frequency sampling method, designs a filter that perfectly matches the desired frequency response at a set of discrete, equally spaced frequency points. Optimality, optimal in the min max sense. Okay, it is not optimal. Okay, ripple behavior creates an equi-ripple response where the error is distributed evenly across the passband and stopband. Over here, the error is zero at the specified frequency samples, but can be quite large between them, especially in the transition. Control over frequency response, provide precise control over passband and stopband edges, allows for arbitrary frequency response shifts by simply defining the samples. So you can understand. So when you are optimizing something, over there the error would be definitely be lower in comparison to the sampling method, because we have already discussed when we are sampling it, we are basically using some finite number of samples to recreate some function. On the other hand, in the Park's McClellan algorithm, what we are doing, we are estimating a polynomial. We are estimating a polynomial, right? So because of that reason, the error is quite minimized over there. Then transition band algorithm designs the transition band for optimal performance. Over here, it is not well controlled and can have large ripples. Okay, design complexity. The first one, it is quite computationally intensive, and the second one is simple and direct method. Typical use cases: the standard and preferred methodology for designing high quality standard filters like low pass, high pass, and band pass filters where optimality is key. And in the next case, it is basically useful for designing filters with arbitrary or complex frequency responses, or when a quick non-optimal design is sufficient. So with this, we will stop today. In the next class, we will be talking about the different types of filters. So you please try to solve this question numerical.